Hi, my name is Max Asselmeier, and I'm a senior at the University of Illinois at Urbana-Champaign. As part of the Robotics Institute Summer Scholars Program in the Bio-Robotics Lab, I'm working on continuous design variable optimization in modular robot synthesis through deep reinforcement learning. Through this video, I'm going to talk about some of the background for this project, as well as some of the methods that we employed, and then I'm going to finish with some of the results that we achieved. So let's start with some context for the project. Prior work used a deep Q network where we would input the goal position that we want the arm to reach along with the arm itself, and then we would receive as output Q values for each module that we could add to the arm. But if we want to change the length of a link, then we would end up with an infinite number of outputs because the length of a link has an infinite number of options. So we can't really use deep Q networks with this problem. So within modular design synthesis, continuous design variables are not being optimized right now through deep reinforcement learning. So now I'm going to talk about the methodology for this project. So we changed the DQN to just output a link without the design variables. And then now what we can do is pass the link as well as the current state of the arm into a variables network that would then set these design variables. So for this variables network, we used the soft Actor-Critic algorithm. And most reinforcement learning algorithms use an objective function pictured here, where the objective J of the policy pi, which is just the actions we're taking, is equal to the total sum of the rewards that we achieve. And these rewards are gained by getting as close to the goal position as possible for our project. But soft Actor-Critic adds on an entropy term, which tries to get the policy to be as random as possible, or to have these design variables be as different as possible. So we implemented these algorithms, and then now we're going to talk about some of these results that we saw. So we began by implementing the regular deep Q network that just output the finite modules to add to the arms. And across 3 training trials of 3,000 episodes each, we were able to have the distance from the goal positions decrease to roughly 2 centimeters. And the raw data points are in light blue, where the darker blue line is just a smooth version of that data to kind of see the trend of the distance over the training episodes. And here we have the total rewards of the network over the training episodes. So for about the first 500 training episodes, the network actually has negative total rewards as the network tries to figure out what arrangements are valuable and which ones are not. And then after that, it's able to consistently achieve a reward of 1, which is earned when the arrangement is able to get within a certain threshold of the goal position. And as we can see from there, the rewards increase linearly. And we also had validation checks at various episodes where we would test arrangements on the same goals and see how those arrangements are changing over time. And as you can see here for some of the earlier episodes, the arrangements are shorter or kind of just more nonsensical. And then as you get later into the training, like for episode 350, you're able to have an arm that is using 3 links to reach the goal. But then by the end of training, the network has figured out that it only needs 2 links. So it's a little less expensive. And these trends are the same for the other goals as well, where you're starting with the shorter arrangements and then ending with arrangements that are able to reach the goals here as well as here. So for the soft Actor-Critic network, we were not able to combine this with the deep Q network. So what we did was we fed the soft Actor-Critic network the same arrangement with 2 links and trained it on a toy problem. And this toy problem consisted of having the length totals and the twist totals fall between a certain threshold where X and Y here are randomly generated, and then the numbers 0.075 and 0.628 were designed so that these thresholds would represent 1/10 of the possible values for the length and the twist. We gave a penalty of 1 if the twist and length totals were not able to fall within the goal thresholds, and if they were, we then just gave a penalty of 0. And as we can see, after about 9,000 training episodes, the penalty was able to fall to a value of roughly 0. For the total rewards, we see a similar pattern as the deep Q network, where after about 1,000 training episodes, the network was able to increase in a linear positive fashion. In the future, we would, of course, like to connect the DQN and the SAC network so that we could obtain this continuous design variable optimization for our modules. I'd like to acknowledge Julian Whitman and how he chose it, as well as the Bio-Robotics Lab for helping me along with this project this summer. And I would like to thank the sponsors for the Robotics Institute Summer Scholars Program for helping me do this research. Thank you and have a great summer.